So welcome. This is Katrina Wyllie's directed research project presentation. So not a thesis defense, but a presentation on the work that she's done. So Katrina has come to us from NOAA. She's a physical scientist, and she's brought with her, I think, a real passion for looking at multi-beam water column data, and particularly to look at wreck lease depths. And she has, I think, done a really nice job of kind of assessing the lay of the land in that regard. And I think she'll talk about why probably NOAA should be looking at this, which is her passion. And also, I think that she'll probably point out that it's going to be difficult to look at it a little bit until some of the bugs and kinks are worked out with the software manufacturers. So it's not really quite ready for prime time, as it turns out. But anyway, Katrina will take us through that. I just gave away all the punchlines.
Thank you all for coming. I'm really excited to see everybody here. I know there's people online listening in too. Hi, Mom. I also want to just quickly say hi to the Atlantic Hydrographic branch. They're listening in Norfolk, Virginia. Hi, AHD. And a bunch of Silver Spring, Maryland people are listening too. Hey, guys, I'll be there soon. Okay, so as you can see from my title, I'm interested in wrecks and their lease depth. What I mean by the lease depth is how much water is over that wreck. And why? Why do I care about this? One of NOAA's missions is to provide navigation products that ensure mariner safety. So we're concerned about the mariner. And we want to make sure that if we're putting a wreck on a chart, we are putting the most accurate representation of the lease depth and position on the chart, so no one gets hurt. So I'm going to focus on the methods of how we find a wreck lease depth. And when I say navigation products, my definition for this talk of navigationally significant is the IHO, the International Hydrographic Organization's definition of 40 meters. So if something's sticking up with less than 40 meters of water above it, I'm calling that significant. So with that, how did NOAA start finding wreck lease depths? Quick history. We'll start with the lead line. The lead on the line, right? You cast it, bring it up in fathoms. What was that?
Shouldn't be going down.
Well, you cast it, and then it goes down. As you can imagine, if you have a strong current, or if you're bobbing around trying to find a lease depth of a wreck, there's some uncertainty associated with this. Lead lines are still used by NOAA today, though, but more to calibrate your multi-beam, kind of give you a good gut check of what you're looking at for your acoustics. In the early 1900s, NOAA moved to wire drags. So this is two vessels with a wire attached between them that you can adjust the depth of. So if you're sweeping like a channel with a wire and you hit something, you raise your wire up and then you go over it again. And if you still hit it, you raise it up again. So you have to clear it by, I think, 2 feet for significant features. As you can imagine, this can take time. Anytime you have something dragging between two vessels, there's safety concerns with that. So in the 70s, we moved to divers and diver investigations. Nowadays, these are rare, but it's a great technique. You get a real person down there, as long as it's safe in terms of the depth and the visibility and the currents. You can send someone down, and they used to actually hold a lead line with a buoy attached on the lease depth of the wreck. Nowadays, as you'll see later in this talk, there's pressure gauges, lease depth gauges that you can use. These are not usually done anymore, but they can be. So they moved away from the direct methods into acoustics and sending sound into water. Side-scan sonar is a great way to detect a wreck. We still use side-scan today to detect wrecks. So what you're seeing here, this is as if the vessel's coming at nadir, shadows are in white. We happen to know what this wreck is. So if you flip it on its side and you're looking at the bows and up, one of the concerns with side-scan sonar is you're assuming a flat seafloor, right? And you don't have, unless you exactly know where your towfish is, you don't have a good depth and position. You can do some trig and measure the shadow length to estimate the height of the mast. But if you just look at this record, I see 2 masts on this vessel. I see one here, and I see a really tall one. I don't think that's real. I think that might be bubbles or something else, line coming up. But how do you know? So a prudent hydrographer would have to say, yeah, if I only have side scan, that's the least depth of that wreck. So NOAA still uses side scan to detect objects, but then acoustic single beam or multi-beam is used to find the position and the depth. So speaking of multi-beam, multi-beam bathymetry has surpassed single beam bathymetry for NOAA procedures as the most common and preferred method to find a least depth of a wreck. And what I want to point out in this slide is that multi-beams can be used in different ways. So if you think about multi-beam bathymetry, each beam is going to have a single solution. So it's either going to be the highest amplitude or the zero phase crossing. For wrecks, they're really shiny, so it's probably going to be your highest amplitude. And another way to use multi-beam is to do the water column trace. So instead of just having one solution per beam, to record the entire trace from the transducer. So what you're seeing here is a wreck of the bow mariner. This is the bathymetry surface. It's a 25 centimeter surface, 50 centimeter surface, apologize. And what you saw is I'll play it again, because that's a cool one. The multi-beam water column data. And I'm pointing out different masts that were not captured in the bathymetry. And some of you sitting in here may say, well, maybe they just didn't designate it, and it's just not in the cube surface. But you can't designate something that's not real, like it's not picked up, right? It's a real mast, but the bathymetry is not finding it, so how can you designate it to include it in your surface? And that's the bow mariner. We'll talk about this wreck a little later on as well. But you'll see this mast, this radar mast, is actually the least depth, and there's a really big one here that was missed in the bathymetry. Okay, so those of you who haven't just had a year or plus of CCOM lectures, I'm going to do a quick terms, just a slide of them. You're going to hear me say significant a lot. And what I mean by significant, I'm going to use it in terms of depth as well as position. Using the IHO, a very standard way of looking at uncertainty, and I'm looking at order 1A surveys. So I'm looking at a depth max total vertical uncertainty. For order 1A, there's the coefficient that doesn't vary with depth and the coefficient that does vary with depth. So D is your depth. So this is 10 meters, 20 meters, 30 meters, 40 meters. Why don't I keep going? Because I'm saying 40 meters is my significant, navigationally significant depth. So if you're at 40 meters, you're allowed plus or minus 72 centimeters of uncertainty. That's what we are saying our data is good at. What about position? Your max total horizontal uncertainty. So this is just for order 1A is 5 meters plus 5% of the water depth. So for 10 meters, that's 5.5 meters down to 7 meters. So you can have that amount of fluff. That's a greater number because if you think about a nautical chart and a rec symbol, you know, that rec symbol is going to cover that distance, but the vertical is the important issue that I'm concerned about. All right, so beam width. When I talk about beam width, so this is just a normalized polar plot of a beam pattern. Here's your main beam in green. You got a bunch of side lobes. We picked the negative 3B. This is that little dotted line to describe what our beam width is at the negative 3 dB level. So you can have like a 0.7 degree beam, a 1 degree beam, a 2 degree beam. It's important to know if you shorten your beam width, you're going to have more side lobes. If you shorten your beam width, you're going to have a better resolution, but you're also going to have a better chance of missing a mast. So if you have a really big, fat beam, you're probably going to find it, but without a really good resolution. You're going to hear me talk about what's the beam width in relationship to the mast. So if you think about this is the main lobe. Well, it's an illustration, obviously. If you have a really big mast, maybe 40 centimeters, and your beam width is 20 centimeters, you expect to find that mast, right? The mast is bigger, so you expect to find it. You expect the main lobe to hit it. If it's the reverse and your mast is smaller than your beam width, you expect the main lobe or most of the main lobe energy to pass it as well as the side lobe energy. So what does that look like? This is a typical Johnson Clark image. So this is a Mills cross, right? So you have a transmit and receive array. When you're transmitting, this is your main lobe, and you've got a whole bunch of side lobes. And then on your receive sensitivity at this angle, this is your main lobe, you got a whole bunch of side lobes. If you look at the intersection of the two, where the beam foresight is, where it's brightest, is your main lobe interaction, right? But you also have main lobe side lobe interaction and side lobe interaction. So side lobes are important. Just to show what they look like with multibeam data, this is there's no wrecks here, right? This is just water. There's stuff in the water, but nothing that I care about in the water. So what I want to show here is this is the seafloor. This here is side lobes seeing the seafloor ahead of their beam. So like this, every line here, I know that's going to make you sick, but each one of these is a beam. This is 7125, so there's 512 of them. So this is side lobes without anything in the sweet spot, I'm going to call it. But as you can imagine, you can also have a wreck in the sweet spot, which is where you want it, right? But because wrecks are shiny, they're made of metal or wood, you're going to encounter side lobe noise from a wreck. You're going to, like decks are really great reflectors, right? So you're going to get high amplitude. And then these are side lobes. So these are all the side lobe range rings. So this is the water column data you're looking at. These black dots represent what the raw bathymetry, multibeam bathymetry solution is at each beam. So this is the problem, right? Because we are getting solutions on our side lobes, and we know it's not real. But in the context of what NOAA collects right now, we collect just the bathymetry. We don't look at the water column. So you get a lot of data like that. Who knows, right? You collect more and more lines, but you're going to get more and more side lobes. What do you do? So I have a solution I will get to. So let's talk about multibeam water column. It's not new. In the 90s, the mid-90s, fisheries scientists started using water column data. It can be used for many other reasons. There was a great review paper that came out this year, and there's dozens of papers that show the relevance of using multibeam water column. And there's one that talks about wreck heights. So of course I zeroed in on that one. And John Clark, so he wrote a paper in 2006, and he said, how can hydrographers use multibeam water column? You know, fisheries can use it, great, but how can we use it? And he listed a bunch of good reasons. You know, surface bubble washdown, looking at contamination from other frequencies and thermoclines, and then wreck delineation. And the example in this paper is an EM710, and what he's showing in, I hope you can see it, there's little yellow dots. That's the bathymetry solution, and the grayscale behind it is the water column solution. So a lighter color, the whiter color, is the higher amplitude, right? And what you see here is the amplitude range plot. So you've got from the transducer, you know, it's in the water column, oh, it hits on something, oh, it hits on something else. Because bathymetry has one solution per beam, the solution for this beam is the highest amplitude right here, which is, corresponds to this deck. So yes, we see that there's a gantry, but because bathymetry, the algorithm for bathymetry only has one solution, it picks the deck. That's shinier, it's flatter. So he took this a step further. He worked with some Canadian hydrographic service employees, and they looked at the GB Church, which is a very well-known wreck. It was sank intentionally, so all the dimensions were recorded before they sank it, which is fantastic for hydro. So that's how we know that this main mast is 40 centimeters in diameter. And he took an EM3002, 300 kilohertz, a 1.5 degree beam. So 1.5 degree beam, they had a range of 10 meters because it actually sticks up really close to the surface, so you have to be a little further away when you survey over it. You would expect the beam width to be 26 centimeters. So the beam width, 26 centimeters, the mast, 40 centimeters. Mast is fatter. We expect the mast to be seen by the main lobe sound, not noise, but sound. What actually happened, the yellow dots again are the raw bathymetry. This one, and this one, it didn't capture the mast, right? Completely not captured. What does that tell you? It tells you side lobes are important. So the energy from the side lobes were coming past here, hitting the bottom, and the solution was the seafloor instead of the mast. This one, it kind of caught the mast and then it arced off towards nadir. Again, if you don't have the water column, what are you going to pick as the least step of this wreck? Are you going to pick this one? No, good luck. So the UKHO, the United Kingdom Hydrographic Office, said, okay, that's interesting. Let's do a study about this. So in 2010, they looked at 17 wrecks. Well, I should say 16, and this thing they made counts as a 17. And they looked at side-scan sonar shadow length. They looked at wire drags, and then looked at multibeam bathymetry and multibeam water column data. And they found the least step from each. They used Keras for their bathymetry and FM midwater for their water column. And I'll get into those softwares in a second. And what they found, if you just look at the bathymetry, which is my bathy, and the water column, WC, there were 3 of those that were significant. Again, significant being greater than the allowed uncertainty at that depth. So, and they weren't just significant by a little bit. Like we're talking 1.7 meters, 2.6 meters, 3.6 meters. And because of this study, the UKHO requires all wreck developments to have multibeam water column turned on. And if the least depth is from the water column, then that has to be reflected onto their nautical chart products. So this spec went into in 2012, and I talked to a guy over at the UKHO, and I said, well, how's it going? He said, well, since the spec, we've had a couple hundred wrecks surveyed, and about 10% of them have these depths that bathy fails on, and then it's really shoal in the water column. So about 10% of the wrecks. All right, so what about NOAA? What are we doing? What are we not doing? NOAA has the capability to collect water column data. So modern multibeams can collect both bathymetry as well as water column data. Here is our hydro fleet. I guess there's actually a few of these, but I listed them as one. So I want to know in my research, can we get similar results? Do we see similar results if we look at water column data over wrecks? And right now, if we look at the software available, can we put this into our processing pipeline to, if we find least depths, to give that depth to the mariner? Like, where do we stand on this? So I looked at 2 software packages. The first one is QPS Blader Mouse. There's a module called FM Midwater. I use version 7.1. If you've never seen it before, it looks like this. You've got your main fan view. You can go in time. You can filter by your dB. So this is your power dB. You can look at beams, ranges, depths. You can figure out where you are with the wreck. The general workflow is on this slide. And I'll just go through it quickly. You create a project. You add your sonar files. Convert to GWC. GWC is generic water column format. So on this step, there's a few options that you can select. Particularly for Reason data, this is where I downsampled in time by 4. So I'm just downsampling in time, so I'm not affecting the number of beams. So the amplitude and the position are still there. But it's just easier to work with the Reason data. You can also concatenate files. So Reason data cuts every gig and makes a new file. So you can actually concatenate those files together, which is beneficial. And I did something else. Oh yes, if you didn't load your navigation files into your .s7k, that's a Reason water column file format, you can load your SBETs, smooth best estimate of trajectory, your navigation source, when you create the GWC file. So you can, if you forgot to load it, you can load it later. The next step is actually not in FM Midwater, it's in MATLAB. I introduced side lobes as a concern for both bathymetry and water column. Tom made a MATLAB code that can handle this, or can deal with the behavior of side lobes, because we know how they behave. So if you go from this picture, which we saw before, the black dots are your real-time your raw bathymetry, not real time, you can take this GWC file that you just created and you can bring it into MATLAB, put in a quick code that takes each range ring, looks at the max value, looks at all the local values. So take the max, subtract 20 dB, which is a pretty common side lobe suppression number. And if your value is less than that, suppress it, get rid of it. So all these white values, well, non-values, I should say, is where the side lobes have been suppressed. So what that does for you is it helps you interpret the data without side lobes. So you can load this GWC file back into player mouse, FM midwater, continue working. If you're using Consberg data, you can basically skip this step because as long as you're loading your sound velocity, your water line, your vessel offsets, and your sys when you're collecting Consberg data, FM midwater will correct the data for you. If you're using Reason, right now it doesn't correct for Reason. So you can use this GeoPick tool, which I'll talk about in a second, to get your least depth estimate. And then if you want to export your data, you want to threshold filter it first. So this is a stacked view, the highest, so all the beams are smushed together and the highest amplitude is being shown. This is the bow mariner, the same one we saw in that video. And then using the tools of midwater, you can filter it. So you can zone in on the rec, and then you can export it. I exported in ASCII as well as the fan time series. Why did I do the fan time series? Because that's your water column data. So if you accidentally filter too much, you can look at your fan and say, oh, you know, I filtered too much. I cleaned out that mast. That mast is actually there. Let me relax my threshold filtering a little bit. And this is imported in Player Mouse, and you can, there's a lot of different export options, but this is what I used mostly was the ASCII point cloud with the time series fan behind it. Another software package and another rec, Keras. I use Keras HIPS 8.1.8. Those of you familiar with Keras HIPS, if you've already upgraded to 9.0, this is going to look different because you just did a big update. If you haven't, it should look similar, very similar. What's new in terms of water column, in the subset editor tab, there's a little water column option now that you can go in, and you've got filters that you can filter by minimum depth, maximum depth, slant range is available, and then this is your intensity slider for dB. So it goes from 0 to negative 64 dB. And then you can display your data just like you display bathymetry, so project vessel day line, bottom detection, you can display by different colors. And the general workflow in HIPS is very similar to bathymetry. Create a project, convert your data, load your tides, your sound velocity, and merge it so they're applied. Compute TPU, your total propagated uncertainty. So that is if you want to make a cube surface, which is just a statistical uncertainty surface, you need to do that. And then in Swath Editor, there's also options to look at the either the stacked view or a time series. You can compare how the bottom detections did to the water column. And then Subset Editor is kind of the meat and potatoes where you really do most of the work. So this is a, it's an area-based editor. So you draw a box where you want to look, and you can load multiple lines of water column, multiple lines of bathymetry. What you're seeing here, you're like, okay, yeah, there's an offset there. Well, the water column's assuming 1,500 meters per second. So as soon as you select what you want, and you right-click and you say add to my additional bathymetry layer, it actually applies the correction for both Consberg and Reason for sound velocity, water level, vessel offsets. And again, you have the similar filters here that I talked about a slide ago. So min and max depth, intensity slider, and you can turn your HIPS data on and off, your water column data on and off. And I mentioned the additional bathymetry layer. That's literally a layer, a Caesar point cloud, and it's easily integrated into NOAA's current processing pipeline. When you make a surface, you can actually just click and say include my additional bathymetry layer, and it goes right into your surface. Again, it's a rec mask, so you want to make sure you designate it if you want it included. and compute the TPU of its accuser. Okay, so let's test these softwares, right? Let's see how we do with a wreck. This is the Troyden. The Troyden is a 90-foot steel clam dredger, hydraulic clam dredger. It's about 8 nautical miles off of Block Island. This is not the Troyden. This is the closest picture on the web of the Troyden. Because it just so happens, so this is the only picture I could literally find of the Troyden is the bow. There's a really popular sub right nearby that everyone goes diving on. So nobody takes pictures of the Troyden. But it is uncharted right now. It will be charted because NOAA found it. The scuba diver community knows of this wreck. The location is published online. But it is described to be a typical clam dredger. So when the NOAA ship Thomas Jefferson went over this vessel, this is their multi-beam bathymetry point cloud. So if you look closely or squint your eyes, you see the stern, right? You see this structure. You don't see these outriggers. And you see something that looks like a mast. Maybe one of these outriggers fell down, right? So I said, oh, this is a great example. Let's look at the water column over this wreck. And what I expected was to see these two outriggers just sticking up there, and that the bathymetry missed them because they have very small mass, and I would expect them to not be found. So, okay. When I looked at the water column data, first I looked at it in FM midwater. So I'm showing you a stacked view of all the beams stacked together, the highest amplitude. It's in the warmer colors. I threshold filtered it. This is also side lobe suppressed, so I had done the generic water column file, threw it in MATLAB, brought it back in. This is my multi-beam water column point cloud, not bathymetry. This is actually the water column point cloud. And what you're seeing is, hey, yeah, that forward mast looks real. And I see the middle mast. I see something kind of sticking up off the middle mast. But what you actually see here is that this mast is the least depth. This is what's sticking up the highest. So I wanted to know, how can I give a number to that mast? How can I say this is the least depth of the wreck? So this was with a Reason 7125. So what I did is I looked at the beam. This is actually beam number 234. And this is the power versus range plot for that beam. So you see it starts with the transducer, water column, it hits on something, and then it hits again. There's a little red dot right there, which corresponds to the black dot right there. So that is what the bathymetry chose for this beam. This hit right here, I would argue, is an extension of the mast. So if we zoom into it, you see the black dots of the bathymetry. And then if you can actually manually zoom in on this peak, and your beam indicator zooms into where you're looking. In the middle of the beam, I geopicked it. So that's that geopick tool I was talking about. So it gives me the X, Y, and Z. So the Z, again, it's Reason data, so it's not corrected for sound speed. It's not corrected for tidal offsets or vessel vertical offsets. So what do I do with that? I actually geopick twice. So I geopick what the bottom detection is here, and I geopick where I think the water column is finding the least depth. I go into Kare's hips and I say, okay, for this line, this beam, this time, what's my correction? What's my actual depth? So I get a correction value. In this case, it was 4.07 meters, and I just add it to my Z value. So I'm trying to minimize the amount of uncertainty by doing that. And for this wreck, here's the bathymetry solution. So that's the actual Kare's corrected depth for this. Here's the water column using adding my correction to the geopick Z value. And I'm saying, I think water column's about 22 centimeters less. What does that look like in Kare's? So you look in the swath editor stack view. This is the same forward mast. Look in subset editor point cloud. Filter that by intensity. Right click, add it to your additional bathymetry layer. And what you get is, this is the bathymetry of one line. This is the bathymetry of one line in teal, and then the additional bathymetry layer in red, if you can see that. So you see there is a red dot sounding that is shoaler by about 23 centimeters. Okay, that sounded familiar, right? Well, if you look at the two together, for the forward mast, here's my bathymetry, 28.96 meters. my Flager mouse, FM midwater, and Kara's hips agree really well within a centimeter. That's awesome, right? That gives me confidence in my kind of workaround that I used in FM midwater. Then I look at the middle mast, I did the same thing, and I still got an agreement within a centimeter. Fantastic. And you'll notice that both of the water column least depths are shoaler than the bathymetry. And the middle mast, they're shoaler by more. And I will show you why. So this is FM midwater. So this is the forward mast. You can see it here too. Here's the middle mast. So we sent divers down. John Kidd, who's sitting in here, and Sam Greenaway went diving in the end of October in Lock Island Sound, which sounds really cold. Very appreciative of that. So this is Sam. He's sitting at the forward mast right now. You'll notice in his hand there's a diver's least depth gauge. So it's basically a pressure gauge. So the procedure, and I'll play the video. This is a short video, but I'll loop it. So the basic procedure to calculate the diver's least depth is to give some kind of indicator with your hand. You just move the gauge up and down so you know on your record where you're holding it on the mast. Subtract the surface pressure, take a CTD cast so you know the density so you can calculate the actual pressure. And then if you integrate the pressure, because if you have more pressure above you, you're deeper in the water, hydrostatics, you can get a depth versus pressure table, and then you know where in your record you are. You can average out how long you held the diver's least depth gauge there. Say that's my depth, and then correct your depth for the final zone tides. I know that's a long explanation, but what I want to say is for the forward mast, we got a least depth of 28.75, and if you look at the water column, we're right on, surprisingly right on. It never happens like that. It was amazing. I actually had forgot to apply the final tide zones, and as soon as I applied it and it clicked in, I was like, oh, this is great. The middle mast, well, it is applied now, by the way. The middle mast is this little pinnacle. So Sam described this, and John described this as about 2 feet tall and like tapering off to 2 inches. So very tiny, right? You wouldn't expect the bathymetry to hit this. Another thing you want to take away, this is the cradles. If those outriggers really were there, that would be bad because we're not seeing them in either the bathymetry or the water column. But they're not there, which is fantastic. So they don't exist. But you do see this pinnacle. And when we look at that in the video, so John was taking the video, Sam was recording the pressure data. So here's where you would see outriggers if they still existed. I think they must have fallen down. As you can see from this video, the visibility was kind of poor. They actually didn't get to the third mast because you're diving. You only have a limited amount of time down there. This is at 30 meters, so we're pushing the limits of our divers anyway, safely pushing the limits. But again, the diver's least depth of the middle mast on the pinnacle agrees so well. Fantastic. Gives us great confidence that what we're seeing in the water column is actually there, and that what we're seeing in bathymetry is not the correct answer with an uncertainty. Okay, so what we just saw in the diving is this structure exists, there's a little thing sticking off it, and there's a forward mast, and that forward mast is the least depth of the wreck. And yeah, that stern is there. So the Ferdinand Hassler went over this wreck. It's another NOAA ship. It's got two 7125s, Raison 7125s. They actually got some side scan data as well. And we know this is still the Troyden because if you look closely, you can see these little boxes. These are, it's a clam ship, right? So one of these actually had fallen off and broke the guy's pelvis. He survived, but we see them. So we know we're in the same wreck, right? We're looking at the same thing. But what's going on with our bathymetry? How come I only have one data point here? Let me spin this around for you. Wait for it. So focus on that one point. I have one single data point. Turns out, with the context of just the multibeam bathymetry, the hydrographer rejected that point. And the submission to the nautical chart, to the Atlantic Hydrographic branch, hey guys, was on the middle mast. And we saw before the pinnacle wasn't selected. So they actually submitted a bathymetry, rightfully so. I wouldn't select one data point. But if you remember, I showed you the Thomas Jefferson bathymetry, and I've got maybe a dozen points on that forward mast. What gives? What's going on? Turns out, oh, we'll spin this one around too, so you can see I'm not lying. Sometimes it's easier to see than 3D. Right, so that forward mast is there. It's in line with the vessel. The divers found it. It's about 5 centimeters in diameter. We wouldn't expect the bathymetry to capture that mast, but it did. And the answer of what gives is acquisition settings are actually really important. If you remember the talk about side lobes can be a pain to deal with when you don't have water column if you're only looking at bathymetry. So when the Hassler collected data, they turned their power and gain down to minimize the side lobe noise. So if you look at their water column data over this rec, we're looking at 3 dB to 22 dB. And you can't see much. You can't see side lobes. You can't see volume scattering. They essentially tuned their water column data to be bathymetry data. And compare that to the Thomas Jefferson. When they collected data, I said, turn your power all the way up. I want to see a high power, 220, and I want to see your gain up really high. Settings they would never use in our best practices right now. And what you see here is the same structure as the rec we just saw in the Hassler's water column. You see side lobes. When you look at the power histogram, you've got 3 dB to 45 dB, so a much greater dynamic range. You can see volume scattering. Basically, you can see water column data. So I ended up extracting the water column point clouds from both the Hassler and the TJ. Thomas Jefferson is the TJ. And what you'll notice on the Hassler, their power is at 198, and their gain is at 15. That's low. And when they went back to develop it, they turned it lower because they were so concerned about side lobes, because they don't want the side lobes to be mistaken for a mast that's not actually there. So if we look at the trade-in with those settings, you focus on that forward mast, we're a little better than 1 point. Remember, the bathymetry had 1 data point. We've got maybe 6 now. If you look at the picture of what the trade-in is supposed to look like, this forward mast was never in that picture. So a hydrographer, even with that information, would likely not select this as the least depth with this information. Take a look at the comparison to the Thomas Jefferson. We got dozens of points, right? We see this mast, yeah, it's there. We see the pinnacle that the divers also found, yep, it's there. But look at their settings. 220, gain of 57. Those are high settings. If you look at this forward mast, I believe it. I would pick it every time. Okay, so that was the trade-in. So I introduced what water column is. I introduced FM midwater and Karis hips. For the rest of the talk, I'm going to use FM midwater, and I'm just going to show you some very quick case studies just to demonstrate that all the NOAA vessels have the capability to collect this data. And what do we see when we process the water column data over these recs? Women's Bay, beautiful wreck. Here's all the bathymetry. This is in Karis. The bathymetry is in Karis. Here's one line of bathymetry, and you can see the rigging. Compare that to the same line of water column data. It's pretty good. The bathy did a pretty good job, right? I see some more information, some more data points, right? But in general, the bathymetry performed well. You'll also notice there's no high aspect ratio mass on this rec because it's laying on its side. The takeaway from this slide is this is the submitted surface. The least depth was selected at 7.62 meters right here. Where I found the least depth in water column was 3 meters horizontally away. So again, within uncertainty constraints, but I think what this shows is bathy can do well, bathymetry can do well, but having the context of the water column, you can actually locate where the least depth of that wreck is. This is the fair weather 7125 data, by the way. Another fair weather example, this is in San Pedro, so LA Long Beach area. This isn't a wreck, surprise. It's an obstruction. It's some kind of oil platform. But I consider it to be like a wreck because it's man-made. It's got vertical structure. It's shiny. It demonstrates where our multi-beam bathymetry can fail, right? So what I'm trying to show here is I actually did find a least depth, about 14 centimeters shoaler than the bathymetry from the water column data on this main vertical structure. That's the span view, that's the stacked view. So my proposal is don't focus on wrecks. It's not just wrecks, it's obstructions, it's dangers to navigation. Anywhere where you could have something sticking out, multi-beam water column can provide context for you to make sure that you're actually seeing the least depth of an object. So Long Branch, this is off New Jersey, New York. You'll notice this is another Hassler data set because they collected side scan, because they turned their settings down, thinking that if there was a mast, they would see it in the side scan and select it in their bathymetry. So this is the bathymetry. This is the bow. This is showing to be the least depth, the area that sticks up the most, and that's what water column also showed. It did have a least depth shoaler than the bathymetry by about 18 centimeters. But what I want to show you with this wreck is all this. It's all this noise. This is fish. Fish are food, not friends, right? Is that the backwards way to say that? Fish are friends, not food? Yeah, they're not friends for water column data because they provide ambiguity. What are you going to do? This is a habitat for fish. It's a very flat seafloor, then all of a sudden you have a wreck there that's sticking up 2 meters. So all the biologists in the room are like, hey, that's habitat. Are these fish ever going to leave? I don't know. If they do leave, you can get a really good picture of the wreck. But if they don't, more work needs to be done to understand fish versus wrecks. And that's a harder thing than you think because wrecks are made up of many different things, different target strengths. And you usually don't know what that wreck is made up of unless you know about the wreck. And that's not always the case. Long Beach, this is another fair weather, Reason 7125 example. Little speedboat, John boat. So I'm showing in FM midwater a beam here. That's the trace here. So from the transducer, water column, it's got a hit, got another hit. The highest amplitude is actually on this deck, but it's very clear that this is real. This is this bow structure here. The red dots here are the bathymetry solution, so you can see again side lobes are not evil, but you have to understand side lobes, they exist. What happened in the bathymetry is there were 1, 2, 3, 4 solutions on this real structure, but it got rejected, rightfully so. I would reject that too without the context of water column data. This is about 5 meters, so we're kind of pushing our horizontal uncertainty at this point. In terms of vertical, we're not looking at too much, about 22 centimeters, but I want to demonstrate that it's the horizontal you have to worry about too. Where on the wreck is the least depth? Lady Cecilia, this was a sad story. You'll notice right off the bat that this is not less than 40 meters, my navigationally significant depth that I'm using. I shouldn't put that in quotes because it's actually an IHO, navigationally significant depth. This ship went down, it got tangled up in crab pot lines, and it went down fast, and all 4 people on board lost their lives. So the Coast Guard needed to find where this wreck was. So they asked the NOAA ships, Fairweather and Rainier, to help them locate it so they could send an ROV down. This data is from the Rainier, which has a Kongsberg, which one? Yes. 710, EM 710, thank you, Glenn. And you'll see right off the bat, you've got sectors. So silos behave differently in sectors. But you'll also see what I'm assuming is crab pot 1, crab pot 2, and crab pot 3. And when the ROV went down, they had to cut 3 crab pots off this vessel. It's really deep. If you look at the black dots, that's your bathymetry. Bathymetry is good at finding the structure of the wreck, but that's what it looks like, right? You just get a blob. If you process the water column data, you can see more of a vessel structure. You can see on the stern of the boat, you've got this, I guess it's the trawl net or some kind of net. You see the vertical mast. This is, I'm assuming, a crab pot. But what I'm trying to show is, yes, this is really deep, but it's just an example of having this data can serve a purpose. Even if it's just a Coast Guard asking, hey, help us find this vessel, you can say with confidence, yeah, this is a vessel. You know, I don't know what this is. I'm not sure. So Bow Mariner, so we saw this video. I told you we get back to it. This is probably the best example of when multibeam bathymetry fails. What you're looking at is Thomas Jefferson bathymetry and Hassler water column data. Hassler was curious about water column and it collected some great data over this wreck. And what I'm pointing out over here is actually the least depth, this radar mast. And then I'm pointing out this forward mast we saw before in the silo discussions is here. What you notice are, again, black dots are bathymetry, and they're not finding the top of these masts. Right? So you can't designate a sounding if it doesn't exist. You need to be able to say, you know, this is the least depth of the wreck. And I'm showing this inflator mouse with the time series fan, right? You can press play and it goes through time. So it's just showing it's real. I see side lobes coming off there, and this mast is real. You know, I see side lobes coming off here. Why didn't the bathymetry capture it? As you can see by the side lobes here, this is really shiny. So just by the nature of the algorithm, it can only have one solution. So it just didn't pick the top of the mast. And it's probably smaller than the beam width. And to remind you what side lobes are, this is what side lobes are. It's very difficult to clean a data set that's like this. This is the TJ's bathymetry data set, not the water column. They didn't collect water column in 2009. But just keep in mind, this is what a poor hydrographer has to look at and say, what's my least depth? I don't know. Right? It just gets very difficult without the context of your water column. And my last example is the Montana. This is a great wreck up in Thunder Bay. You know, fresh water, so wrecks stay nice and preserved, and you can see them. So there's a lot of dive video over this wreck. So this is the Montana. It's a side wheel steamer. It burned down, so like this tall mast burned down in a fire. What you do see is an engine, which is this engine right here, which you can kind of see in the dive picture. And you see a boiler. The boiler's still there. And what you think are side lobes, here, here, and here, are actually part of this structure. I'm assuming it's part of this structure. And you can kind of see it in this dive video too. There's a piece of the, I don't know what material it is, but a piece of it sticking up here. So this data was collected by NRT4, Navigation Response Team 4, with an EM 3002. They were updating the nautical chart. They were also helping Thunder Bay Marine Sanctuary manage their sanctuary. So earlier this year, there was a Project 6 Fathom Bank project, and they, Fish and Wildlife, I guess, wanted backscatter data. So NRB, Navigation Response Branch, said, hey, we've got a new EM2040C, a Kongsberg sonar. You know, it's in the box still. Let's take it out of the box. So they took it out of the box, and they collected data with it, and they happened to turn water column on over these wrecks. And I got my hands on the data, and this is what I got. So this is the water column point cloud with the time series fan. You see the engine very well. The engine's fat, right? It's fat and it's flat. So you expect bathymetry to capture it. And if you look at the NRT bathymetry compared to the water column from this year, you're looking at a centimeter difference. You know, it matches. We expect bathymetry to do well here. What I want to point out, though, is there are other masts on this vessel. And you know, this is a real mast, and it's not being captured. So even though it's not the least depth, which is that big fat engine, bathymetry still misses mass, right? And this is meters tall. So this is completely missed from your bathymetry solution. Why? Because one solution per beam. This is pointing inward, right? It's flat. It's got a higher amplitude, so that's your solution. Okay, so my results. There's a lot on this slide. What I just want you to get out of this is bathymetry, water column. Bathymetry minus water column is the difference. The differences are all positive. So water column was always shoaler than the bathymetry solution in every one of my examples. Other things I want to get out of is I saw 3 examples of where the least depth was selected by a hydrographer that was meters away, 3 to 5 meters away from where the actual wreck least depth was. I highlighted in bold the significant differences. Just to explain this one, this was the Bigelow used ME70 in bathymetry mode, but they did very well at finding the forward mast of the Troyden in their water column data. And then the Lady Cecilia, yeah, that one was deep. So my best example is the Bow Mariner. And if you remember the UKHO, the United Kingdom, they said about 10% of wrecks, are going to fail. And I say, yeah, I kind of agree with you. Where they're going to fail, they're going to have mass, very high aspect ratio. And the water column data is going to show that, and the bathymetry data might not select that mast. So I've got 4 challenge slides. We've talked about all of those. I kind of cheated, and I put a challenge in the solution on each slide, or I tried to. We talked about side lobes. So there's transmit and receive side lobes. What you're looking at are the kind of like ghost images. It's the transmit side lobe, so you kind of see it coming before it's there. What's great about this is in each hyperbola, there's the maximum is at the peak, right? The highest amplitude is going to be at that peak, so you know this is all fake. So that can be filtered out easily. And we talked about Tom Weber's MATLAB code that just goes down each range ring, and knowing the nature of side lobes can suppress them. Another way to minimize side lobe contamination is to survey in the sweet spot, right? Your sweet spot is defined by your minimum slant range. So if you're planning a line over a wreck, try to go over the top of it if possible. Don't hit it. If you're not sure about it, start over to the side a little bit and then move in. And then another way to minimize side lobe issues is, I think Kongsberg does this, Reason does this in their multi-detect algorithm, but suppress those side lobes in the bottom detection algorithm, or at least integrate a side lobe suppression into your software, your processing software that is user-defined. So if 20 dB, which is the side lobe suppression I used, isn't going to cut it, maybe 15 is better for your situation based on your target strength and the area that you're looking in. We talked about ambiguities. Fish. Yeah, not much you can do about that right now. More work needs to be done to minimize the ambiguity between what is actually wreck structure and what's a fish, what's a crab pot, kelp. They've got little air bubbles too. So that ambiguity still exists. I don't have a solution for that one. Multiple reflections. I saw this a lot in the Kongsberg data, just the one data set. I think what you're seeing is, so this is the engine, this is the Montana, the Thunder Bay wreck, and if you look closely in the water column, you see a multiple, and it's actually, I think, a multiple of the ping before it. Because if it's like a side scan multiple, you see it, further down here in the range. These are 2 different time slices. But that can be confusing, can cause ambiguity. You also see, this is the boiler. This is the transmit side lobe of the engine, this engine that's coming. And then the whole thing is a multiple in the water column, right? That's confusing. So you just have to be aware of side lobes and their behavior when you're looking at water column data. And just be aware that they exist and brush up on your acoustics if you need to. And then multiple reflections. Sorry, another example of multiple reflections we saw in the Troyden. This is some kind of weird side lobe behavior or maybe an aperture failure of the sonar itself. But if you look really closely, you can kind of see a Troyden here. There's a Troyden here. If that is loud enough, if it's got a higher amplitude, it can confuse what you're looking at, right, when you go to select the least depth. My last challenge slide is acquisition settings. As we saw from the Hassler data, settings are important. If you turn your power and gain down, not only can you miss the feature in your bathymetry, but you can also miss it in your water column. So if you're running around with low power and gain, you might miss a feature that's there that you don't know to go back and collect more data over it to begin with, right? So a kind of solution for this is to either enhance or make use of your real-time acquisition visualization for water column to say, yeah, I see volume scattering, I see side lobes, that's what you want to see when you're collecting this data. So you can actually make a differentiate between what is rec and what is water column. You can't really do that here. Oh, I lied. There's another one. Data size. I get this all the time. Data. It's so much data. I can't handle it. So I looked at the size of my files versus the length of time to get a data rate, and I'm seeing Reason water column data to be about 3 gigs a minute. And a side note there, I'm not using, none of the data sets that I had the newer Reason datagram, which is expected to reduce the size by 20%. But if you compare that to Kongsberg water column data rates, it's about 2 orders of magnitude lower. These are just my 6 or 7 examples, so it can vary. But the solution to this challenge is I'm not saying to collect water column all the time. I'm saying years from now we should be doing that. But right now, it's kind of we know the recs there. We're really good at finding recs with bathymetry. So if you found the rec, when you go to develop it, collect additional multibeam data, plan your line so you're directly over it if possible, safely possible, and turn your settings up. Turn that gain back up, turn your power back up, because we can handle side lobes in the software that we have. We can deal with that. And multi-detect is also multi-detect is real with the Reason T20P and 7125, the new feature packs. I've heard rumor in Kongsberg that they're coming out with one as well. Basically, this says for each beam, instead of just finding the highest amplitude, find me up to 5 solutions. So theoretically, you could find the top of the mast and the seafloor below it. It needs to be advanced, right? It's new. It's up and coming. Where I see this going personally is some kind of indicator where you run multi-detect all the time, and if you have more than one detection, switch into water column mode. I think this, the question is, how many points do you need? Is 5 enough to say, yes, that's a mast? My answer is you need the whole water column. You need that context. You need the fan. 5 detections per beam without context is just more noise. It's more of a headache for the hydrographer who has to try to find the least depth. And I stole this picture off of Reason's website. This is a rec without multi-detect. That's the rec with multi-detect. If you look closely, you can see like a davit. It's essentially a very filtered down version of water column data. Okay, so in summary, I have 2 summary slides. Yes, bathymetry can miss mass. If it does miss mass, it can be significant by meters. We're talking not just like barely significant in terms of depth uncertainty, but meters. And about 10% of the time, I agree with that number, if you have a mast, you're likely to miss it. And the water column data provides that context to the hydrographer. So this picture is the Bow Mariner again. These are those masts that we talked about. This is the Woman's Bay wreck. It's on its side. It doesn't have vertical mast sticking up, but where we selected the least depth was horizontally, not actually the least depth of the wreck. And then software packages. On their own, they're not complete, but pieces exist in each of them, and outside that are hopefully going to be realized soon. But in light of that, as they are now, I would say, hopefully you guys would say too after listening to this, is that NOAA should be collecting water column data over recs when we develop them. Mind your settings, make sure you're actually getting water column data, but there are workflows that exist that can get you at least depth from the water column data, and it performs better than bathymetry. So this is our good old Troyden with that forward mast, and this is the Montana with the engine, the boiler, propeller. These are all the water column point clouds. And I just want to acknowledge a few people before I say thank you. NOAA's Office of Coast Survey, thank you. Tom Weber and Andy Armstrong, couldn't have done it without you. My fellow graduate students. These people I list all either got me data or sent me data or looked at my slides. I should probably add my mom in there because she can probably give us talk better than I can at this point because she's heard it so many times. And then the captains and crews of the ships that collected the data. I really appreciate it. This research project obviously wouldn't have happened if you guys weren't so willing to get me data and being interested in water column. So thank you.
know what UKHO's process is? Because you said they were using Flater mouse and FM midwater or whatever.
Yes.
You had to do your weird geo. Are they
Yes.
doing something similar to that?
So I hopefully improved on what they had presented. They were actually measuring from the seafloor, so the height of the wreck. They were saying, they were measuring like the DZ, the difference in Z from the bottom of the seafloor. So I wanted, and I don't know actually how many Reasons versus Consbergs they have, so it's not an issue with Consberg data, it's an issue with Reason data right now, because you don't have that interface to say, I want to apply this sound velocity cast nearest in time or nearest in distance. That's not part of the Reason record right now, and it can be part of the Consberg record. So yeah, I tried to minimize that uncertainty by finding the detection closest to where I thought the least depth was. Some of the cases where I looked at two different vessels, I did look at the actual height of the wreck, like from the seafloor to the mast, and those have greater uncertainties, obviously, but that is similar to the UK event, at least in 2010 when they wrote that paper. Does that answer your question?
Yeah.
Questions?
So the Hassler and other ships are driving around with the gain turned and the powers turned way down, I think for the express purpose of not having a bunch of side lobes in the bathymetry they have to worry about.
Yes.
Are they collecting seafloor imagery at the same time in order to maybe identify dangers to navigation that they might have missed? And are they specifically looking at the imagery in order to do that?
So the Hassler's best practice is to collect side scan sonar data to capture anything they may miss with the low power and gain settings. You're exactly correct. The issue or the concern they have is side lobes, and if they don't pick, if they are rejecting the side lobes, maybe somebody at the review, the Atlantic Hydrographic Branch or Pacific Hydrographic Branch may say, oh, that looks real. I really think that's real, and I'm going to select that. So they're collecting side scan at the same time and hopefully going to say, yes, there is a mast here. I should select that one single data point because that's probably the only hit I got on it. If they're looking at it, that's a good question. I think they are.
What's your recommendation? How should they be driving around with the lower power settings to avoid those problems with the bottom detection algorithms and the sonars that are giving all the side lobes, and then turn them up only when they run over wrecks? Or what should the procedure be?
I think our bottom detection algorithm should be better. I think we should use the behavior of side lobes in our algorithm, so we are not selecting on side lobes. So
okay, but
yes,
you're going to make them.
I'm not going to make it do. No. So I guess
given what you have.
I understand. Well, he asked how I would do it. That's how I would do it. Sorry. So I understand your question. I think the procedure-wise, or procedural, is that the right word? Running with lower power and gain, you get really clean data. It's easier to deal with. You're not worried about side lobes. The Hassler data always looks really clean, but you run the risk, right? You run the risk of missing things. So I think there has to be, I know like Glenn has a SatMon and people are using that, so we don't want to oversaturate our backscatter, but I think there should be a closer look at what our settings are, and I think the settings that some vessels have are too low all the time, and that we run the risk of just missing things completely to not even know to collect them. And if you're not, looking at your side scan trace, I think they just collect side scan on development. It's not their main scheme. So you could miss a feature completely. But is that risk worth messy data or more messy, more side lobe noise? I don't know how to answer your question. Fix the algorithm.
Yeah, it seems like that there's a good reason to use seafloor imagery there as well to help identify things you might otherwise miss.
Yes, yes. And I'm not trying to say the Hassler is bad. They great job, great imagery. And they're conscious enough to collect side scan sonar when their settings are low to look out for masks. Yes.
So we have, through the years, occasionally stumbled on objects that are like masts that aren't connected to a big wreck. It's just spud barge pile or something like that that's sitting in the water column. It seems to me that if you're not running the water column all the time, your opportunity to detect those things, particularly if you're running at the lower gain settings that we talked about here, goes way down. Isn't that an argument to run water column all the time?
Yes and no. I think if we tried to run water column all the time, we might run into storage issues on the vessels, just with the amount of data that's coming on, unless we don't save it. As long as we're running it, someone's looking at it immediately and saying, no, nothing's there, you can get rid of it. If you have something like a spud barge, I think you used, I would expect that to be loud enough to get a few hits on it. And you know, if we're going to go develop that anyway, if we say, oh, hey, there's something really weird, let's go develop this, then you could turn your water column on.
It might just not get rejected by the hydrographer like those masts did.
Yeah, so
Just be a spud, right? Not
yeah,
large
yeah,
spud,
exactly.
so
Well, so I mean, our procedures now are, we go back and collect data anyway, because we don't expect our bathymetry to find the right answer the first time. So our procedure is to go and get development. So I would love to run water column all the time. I think it's got a huge benefit for fisheries and all sorts of other sciences, but I don't think we're there yet. That's where the multi-detect kind of can come in and say, okay, I've got a whole bunch of detections on the seafloor as well as in the water column. Something's here. I'm more likely to see that in a multi-detect solution than I am in a single bathymetry solution. I don't know if I answered your question. Okay.
you can't go.
I'm not sure I
You
agree.
can't go to the
You would want to collect it all the time? I would.
I think cheaper than another crew. I recognize the problems.
Well, because ship time's expensive, right? And you know, my physical oceanography professor is like, okay, that's great. Why do I care? It's Rex. I was like, well, you should care because if we start, you know, going out on ships and collecting this data, it's NOAA, so the data is available to the public, so a whole bunch of other people can start using this data. So I see it going that direction. We just need to get NOAA to first require it or put it into the specs to start collecting it. So that's where my push is, to show it is valuable. So let's start collecting it in developments, and maybe that'll progress as the software progresses. Right, that too. Hi. Yeah.
I may be confused about what you're talking about backscatter versus side scan sonar, but my question really is, did you look at the actual multibeam backscatter, the full time series of the backscatter, and that's what you're calling the side scan?
No, so side scan, that was
Traditional side scan.
traditional side scan, just intensity of the return, you know,
So
no
my
angles.
question is then, when you had the bathymetry, did you also look at the full-time series backscatter and compare that to what you found in terms of mass and so forth? Because you can really process that at a much higher resolution than the bathymetry.
Right, so the water column would be the entire time series trace per PV.
No, just the bathymetry. Just take the multi-beam full-time series backscatter. So it's a backscatter sampled across each footprint.
Okay, I see what you're saying.
Yeah, but much higher resolution than the bathymetry is. And see what you get in that, because that comes free, basically. Just record the backscatter.
And we are doing that, Glenn.
You're talking about the seafloor.
Seafloor
backscatter.
The seafloor,
backscatter.
yeah.
Yeah, so I think all of our surveys actually collect acoustic or seafloor backscatter now, and the branches are processing it. And it's a product that we're giving to.
And so,
but it's not processing.
Full-time series doesn't show you anything any better than what the bathymetry was showing?
Well, it's showing you the seafloor. I think the concern I have is in the water column itself. So before you get down there.
If it gets a hit off of, if the backscatter for the multibeam sees a mass sticking up, it's going to think that that's the depth. So just look at the backscatter, and if you see a bright, high backscatter value, that's not where you think the normal seafloor is.
Is that the way the interferometric systems work? They take backscatter and process bathymetry? Is that the whole process?
But if there's no depth kick on the mast, the way at least Resun works with snippets, it's not going to record around the mast. If there's, like in the case where you have a one ping, that one ping will have it, but
or you're missing a
you're
mast.
going to miss
Well,
something on it.
but for each footprint, at least in a Koonsberg system, it does a time series, a much higher time series across that footprint. And so if you look at the backscatter image and cross it at 25 centimeters or something like that, and you'll see maybe a bright spot on the backscatter that would not correspond.
Can you go to one of your full time series? What
The filter gives you one value, but the backscatter can give you much more.
You show the intensity
But
of
it's still
just one beam.
The what?
Oh, yeah.
Yeah, it does.
Yeah, I think Damien's right. If you don't have a bottom detect near the target in the water
So,
column, you're not
yeah,
going to get any
that case
snippet
right there.
data from it.
Yeah, you're not gonna get anything.
So where the bottom detection is, you're only getting samples on either side of that bottom detection. You're not getting that first return, which is what she's saying.
Oh, I see what you're saying.
Yep.
If you don't get a zero crossing on the phase,
Or
wherever you get it, and you're sampling on either side of that?
yeah, those samples are only on either side of the bottom detection.
Okay.
You might get a shadow where you don't get anything on the C4.
Yeah.
You could get that, and if you were in a resonance system, you collected side scan data, I believe that is not coupled with the bottom detections, so you might see it there.
I did not look at that.
The shorter answer.
Yes.
I just, you mentioned the UKHO, and that was from a procedural point of view with NOAA. I mean, the UKHO used to white sweep or vast,
Yes.
white sweep or direct, so they had a significant reason to change to using something else.
Yes.
What is the NOAA? Does NOAA have the same sort of real reason to change or not? Is it, you don't white sweep, but is it always a diver on a wreck, or how do you now get the lead?
So the procedure now is just multibeam bathymetry. And that's, from I think 2005 was the last time I actually saw a diver lease depth. And I never saw the reason why we went away from more direct measurements like wire sweeps and divers lease depths. It just kind of procedurally said, oh, hey, we've got these new systems that are really good. Let's use multi-beams.
The safety overhead associated with diving
Well,
would be
that
pretty
too.
significantly.
Yes.
less than.
And time. So, you're looking at hours to get a lease depth when you're wire dragging or sending divers down, whereas if you want to cover more ground, you've got your acoustics. So currently NOAA's best practice is multi-beam, but in the specifications, it still says you can use a diver's lease depth. Wire drag's not listed. You can use a lead line or a sounding pole if it's clear water, right? You can see the lease depth, okay, it's right here.
It seems like you have a technology challenge. You can the technology can show you're actually getting better now and getting the least depth, but you don't have the economic, if you're not actually wire sweeping or diving, you don't have the real, so much of a reason to change, I guess. Technology you do, but not from, that was just a comment.
No, I agree with you, but I think to reiterate the point of where we do fail by meters is it might not be economic, but it's safety. And I think the mariner safety, like NOAA's mission is making sure our mariners are safe. And if we can say we have the technology to do this, it's only going to be a few gigs extra if we collect this data over the wreck. Why not? And I think specs can change, right? They're not written in stone. So if we can start saying, yeah, we can find things in the water column now, maybe that's where things are going.
Well, there's a big economic benefit. If you miss a mast and a port and it gets shut down so you go figure out what's going on, that's a pretty big.
I actually have that slide, that picture. Actually, last night as I was preparing some of these slides, this happened. This is really exciting. Something came up in the bathymetry in a port, and they're like, hey, we only have the bathy, but we collected water column. We're about to shut this port down. And I said, oh, okay, I'll look at it. I don't have the answer to this yet. I looked at it.
Obviously, a giant squid.
Obviously, obviously. But yeah, economic, if we didn't have water column data, we'd be like, hey, that's a deton, shut the port down, thousands of dollars a day, right? So we have better technology. All of our vessels have this capability to collect the data. Our software is getting better and better to process the data. So we can store the data better because data storage is just getting better. So I'm just trying to say, let's start doing this. Start collecting.
Well, where was this?
I blame B for this. This is the 2040 data in the Thunder Bay area, so it's in the lakes. I forget, it's like some calcite, I don't know.
Freshwater giant squid.
Freshwater giant squid. Yeah. This was an add-on slide. I don't know what that is.
Godzilla.
Yeah, I was going to say, Godzilla.
Said Jim.
It's weird, right? Right, but you know that economically that could be important.
Especially if it's Godzilla.
Especially with Godzilla, we found it. Any other questions?
Just note that I think some people are going down to celebrate and just have a beer down at Wylie's in
Please join us.
15 minutes or so.
Yeah, hopefully it didn't go too long, but I appreciate the questions and thank you very much.